Hello, I'm excited to tell you about sequence abstractions for flexible line rate monitoring. Modern networks have become extremely complicated and hard to monitor with a variety of different pieces of hardware and protocols floating around everywhere. And as we've seen in this talk, programmable networks have made this problem even worse. New protocols are developed every day, and you can implement them immediately on a programmable switch. One good way to monitor these networks is to track sequences of network events like packets. And so we've developed a simple language that allows users to use the flexibility of programmable switches to easily express a wide variety of network sequence monitors. So what I mean by network sequences is something like port knocking, where the server is recognizing a literal sequence of packets coming to different ports from the client. In this case, these are the numbers on top. And then if it sees the right sequence, it will open the firewall for the client. In video fingerprinting, the sequence is different. In this case, it is a sequence of packet sizes. So here, even on encrypted data, the sizes of the packets that a client sends and receives can be used to indicate which video or which service that a user is using. In-network applications, like chain replication, which is shown here, many sequences arise, such as those to write or commit or distribute data around the network. And in networking protocols like TCP or DHCP, there are sequences such as handshakes. So a sequence monitor is a system that recognizes a pattern of network events like this. And if the event sequence can't be recognized, then that could indicate an error in the network. So recognizing them usually boils down to running a state machine over a sequence of packets and accepting or notifying when a certain sequence arrives that violates the protocol. I'm going to show you FLM, which stands for Flexible Line Rate Monitoring, which allows programmers to use the flexibility of programmable hardware to run sequence monitors in current networking switches at line rate. So as an overview of the FLM system, the user provides their input, which is a specification of some network sequence that they're interested in, as a pattern that looks kind of like a regular expression here. This is handed to our FLM compiler, which turns it into a state machine, as well as some additional state tracking code, and then uses program synthesis to generate a microprogram that can run at line rate on the switch and recognize the state machine. We've provided a definition of the syntax and semantics for this pattern language. We have a proof of correctness of our compiler from the pattern semantics all the way to P4. And we've evaluated this pattern language on 15 different networking applications. So next I'm going to show you through walk you through how a programmer would write a FLM program to detect anomalies in the DHCP protocol. DHCP stands for Dynamic Host Configuration Protocol, and it allows servers to hand out IP addresses to any number of clients for a temporary amount of time. The DHCP starts with a client sending a discover message to the server asking for an IP. The server responds with an offer message with some IPs it has available. The client replies with a request asking for one, and then the server replies acknowledging the request and assigning the new IP, in this case 1234. From there, the client has an IP now, so it can go and send traffic to the internet, do whatever it wanted to do with this new source IP. Say, for example, that an operator was worried about clients misusing this protocol or bugs in the protocol. A misuse would look like a client asking for a IP and getting it acknowledged, but then using a different IP when it communicates over the internet. So to specify this misuse, the user will first specify which events they care about. In this case, the first event we care about is this acknowledge message, because it has the new approved IP for the user. This contains the client IP and then the MAC address, which we'll use as the identifier. And then our other event is just everything else. So this includes both the initial handshake messages as well as the internet traffic that the user is supposed to send afterwards. Next, the programmer in FLM will come up with a pattern that specifies the sequence that they care about. In this case, here's an initial attempt or basic pattern. Use of the DHCP protocol looks like some packets at the beginning to some other packets to indicate the handshake, followed by an ACK message, followed by some more packets that would be the network traffic. This doesn't really specify the misuse yet. This is just basically any use of the protocol with an ACK message. So to specify misuse, we have to record the client IP in the acknowledge message. To do that, in FLM, we use what's called a binding. Use the special character @ and then bind the variable assigned to the client IP parameter in the ACK message. So now this client IP can be used later in the pattern to check that the user of DHCP is doing the right thing. To check that, we use what's called a predicate in FLM. So here, instead of just having any number of other packets for the traffic, we'll have some packets that follow the protocol, so they're using the right IP, followed by some packets that are not following the protocol, so SIP is not equal to assigned. Okay, so that's our FLM program. You can see it was pretty simple to create. So the user first declares the event types that they are interested in. That pattern that we came up with only monitors misuse for one client. So obviously the server wants to check all of the clients or many clients at once. To do that, you'll declare a spec of size, well, any size, but in this case 2048. So that means it can monitor up to 2048 MAC addresses at a time. And then the user will define some index into that space. In this case, it's just hashing the MAC address that was in both of the events. Then you'll say detect. You give the pattern, which we just came up with. And then finally, you can have some real-time response that the switch will run as soon as a match is identified. So this could be either dropping the packets, adding the user to a list, or sending an alert or something like that. So next, I'll show the compilation steps overview for this program that we just came up with. So we'll start with the pattern, because the pattern is the most complicated part. You are given a pattern which has bindings and predicates in it. The first thing you do is remove this binding code, because on programmable switches, the most complicated part is the state management. So you remove the bindings, and you come with a little program that handles variable updates and things like that. So in this case, there's only one variable update, which is to set the assigned variable when an ACK event arrives. And then you have a binding-free program left over that you'll turn into a state machine. This is still a little too large, so we'll next remove the predicates from the binding-free program and turn it into a regular expression over a finite alphabet. So in this case, we have replaced these two predicates, source AP equals assigned and not equal to assigned, with two different characters, other with the predicate true and other with the predicate false. So now that this is just a regular expression, the next step is to turn it into a DFA, or state machine, and then synthesize its implementation in P4. So let me tell you about how we embed these state machines. This is a picture of the state machine for the DHCP pattern we just came up with. It starts by waiting in the initial state for an ACK packet to arrive. Once an ACK packet arrives, it goes to the ACK state. If other packet arrives and it has the wrong source IP, it will go to the accept state, and otherwise it'll reject. So misuse of the protocol would be going to ACT and then the wrong source IP coming, so that's the accept state. So implementing this on the switch is actually not trivial. For example, if you just represent the states as numbers 0 through 3 and then have a big if statement or match table to implement it. This is far too large for the Tofino switch to be able to implement in one read, modify, write action. So if you want to be able to update the state on every single packet, this program is too big. So, and this is difficult for any high-speed pipeline, not just the Tofino, especially for a larger state machine than this little one with only 4 states. So we have to come up with a way to compress this. We do this by renumbering the states. So if you number initial as 0, act as 9, accept as 7, and reject as 1, and then you renumber the characters, say giving act 12, the wrong source AP2, and the other 0, then this little microprogram here, which only has 2 lines, or well, 2 branches, actually implements all 12 of the transitions that are possible in the DFA at once. And just to kind of prove that to you, if you start in the initial state and we get the character act, this should end up in the act state. So initial was mapped to 0. The character act had the number 12, and that is bigger than 9. So 0 plus 12 is bigger than 9. So we're returning the input XORed with 5, which is 12 XOR with 5, which you can just believe me is actually 9. So programs like this are extremely hard for programmers to come up with, obviously, because you have all these weird bit tricks and stuff. So we offload all of that hard work to a SAT solver. If we come up with a logical formula that represents all the possible microprograms on the switch, and then we encode each of the transitions in the DFA as constraints. If the solver comes back with an answer, that gives us the numbering of the states, the numbering of all the characters, and a little microprogram that can implement the transitions. OK, so now we're left with just P4 code. So we hand that off to the vendor-provided P4 compiler, and it runs on the switch. So to evaluate FLM, we had 2 criterion for what we thought was a useful sequence monitor. Sequence monitors should be both flexible, so they should be able to implement a wide variety of sequences that appear across the network. And they should obviously run at line rate, because otherwise you can't examine every packet, and so you might miss some sequence matches. Our questions were whether FLM can be used to write a wide variety of programs, and then whether or not the compiler works in a reasonable amount of time. So for our evaluation, we implemented 10 different FLM monitors, and we had varying network services from simple protocols like DHCP, which I just showed you, to monitoring complex network applications. So for video fingerprinting, again, we were monitoring a sequence of packet sizes. For port knocking, we were monitoring the destination port of packets. For DNS checks, we were monitoring different things that could go wrong in the DNS, basically handshake. For distributed storage, we were looking for the wrong forwarding pattern. And for Paxos, we were looking for the recovery sequence. And for the ML training, these were for in-switch aggregation. We were looking for errors in the aggregation algorithm. So these compiled into a DFAs with between 4 and 19 states and between 2 and 32 different symbols. Here I'm showing the lines of code that it took to write the FLM monitor, and then the outputted lines of P4 code, which is kind of a proxy for how long it would take to write the monitor by hand in P4. As you can see, it only uses between about 30 to 40 lines of code, even for complex patterns. And also, there's no guarantee you would be able to come up with the DFA implementation on your own anyway, because it has all these weird bit tricks in it. And then for compilation time, I have just the time it takes FLM to compile the example, and then the time it takes for the vendor-provided P4 compiler to take that output and write machine code. And it usually takes about 2 minutes. There's one outlier here, which is about 10 minutes. So it's pretty reasonable. So in summary, I presented FLM, which is a pattern-based language for specifying sequence monitors. I showed you a series of compilation steps to network hardware. And in the paper, we've proved that this compilation is correct and preserved the semantics of the network pattern language. And we evaluated the system for ease of use and efficiency. Thank you.